Okay, so let's look at continue our discussions related to biasing of BJT amplifiers. And in an earlier lecture, we had seen that there are several different ways of biasing a BJT amplifier. One of them is what we call as a fixed resistor bias, the circuit shown over here. And this particular circuit is very simple. The biasing is what you do is basically use the supply voltage and RB to fix the value of IB, and then IC is equal to beta times IB here. VCC minus VB by RB is the IB here. The other one is the voltage divider bias, where you use R1 and R2 to create a voltage at the base here, and that results in a voltage at the emitter, and then it causes a current to flow in the emitter, and the same current almost flows through the collector here, and so we get this particular expression here. And the advantage of this particular expression is, and this particular method of biasing compared to the fixed resistor bias is that this circuit is beta insensitive here. Now, the reason why we are discussing this biasing in a little bit more detail is not because this BJT amplifier and this way of biasing is very, very important. The reason is that it carries some important lessons, and through these simple examples we can understand those larger themes that are there. And one of the things is that, you know, when this particular circuit voltage divider bias is presented, it is presented as the best way of biasing. Many times you may hear that the best way of biasing is the fixed resistor bias here. Best way of biasing, right? And I'll put it under quotes here. And it's presented as if it's a very robust against variations. Robust against variations. So we have said that the circuit is beta insensitive, but that's not the only source of variations that are there here, and we'll look at that in a little bit more detail here. And the other thing is a general engineering outlook which is there, is that when you gain something, you invariably, many times you end up losing something. So this particular circuit that we have here, this particular circuit is giving us insensitivity to beta, right? So the circuit, the bias current is much less sensitive to changes in the current gain beta of the transistor, and so we're getting something. It's giving us some benefit. Now, in general, in engineering and in elsewhere also, we find that when you gain something, you lose something also. And so, in many of the discussions on this voltage divider bias, all the positive aspects of voltage divider bias is presented, and is presented as if it's the best way of biasing here, and is very robust against variations. And the other side of the story is not presented, that when you gain something, you lose something also, right? So let's look at those aspects in this particular discussion. All right, so just to remind, beta sensitivity can be understood from this particular set of calculations. So for beta of 100, so when you take beta of 100, this particular circuit is designed to give you 1.76 milliamperes here. And the other circuit here, voltage divider bias, is also designed to give you same value of almost the same value of ICQ here, 1.74 volt here. And the rest of the parameters you can see here, VE is 3.16 and VB is 3.87 and VC is here. The other details are given here, right? And so we can see the beta insensitivity by redoing the calculation by, let's say, taking beta equal to 200. Now in the first circuit here, the ICQ simply doubles, because ICQ is, as we can see here, is directly proportional to beta. So earlier we had 1.76 and now we have 3.52. So it simply doubles, and there's a 100% change here. On the other hand, in this particular circuit, when we do beta equal to 200, we get ICQ equal to 1.83 milliamperes here, and we'll get only 5.2% change here, right? So compared to a 100% change here, we get only 5.2% change here. And that's why we say that this particular circuit is insensitive to variations in beta. Now 5% change for some application may be still significant, and you may want to reduce it further, and that we can see from this expression for collector current here. So if you want to make it more insensitive, right now the factor RB by 1 plus beta, if I take beta equal to 100, is 0.175 and RE is 1.8K. Now if you would like to make the circuit even more insensitive, we could, for example, if you don't want to change the value of the collector current, you could make RB here even let's say 10 times lower. And as you make RB 10 times lower, the circuit would become even more insensitive to beta. So depending on the requirement, one can make it, the sensitivity to beta can be altered by basically looking at this factor here. How large is RB compared to RE here? So looking at this particular factor here, we could adjust it. So now beta is only one thing which can cause the bias current to change here. So for example, if we look at both the circuits are there before us, and if we look at, for example, let's say circuit number 1, let's call this circuit 1, and let's call this circuit 2. Okay. So circuit number 1, for example, the base resistance. If we look at base resistance, normally the resistance, if you go and take a resistor in the lab and build this particular circuit, the resistors have tolerances. So for example, this particular resistor, depending on the resistor that you choose, it could have a tolerance of plus minus 10% or 5% or things like that. Similarly, the collector resistors will have a tolerance of plus minus 5%, meaning that the base resistance could be 5% higher or could be as much as 5% lower than 470K. Similarly, on the circuit 2 side, the resistors R1, R2, RC, RE can all have a tolerance of plus minus 5%, right? Let's say, as an example, 5% we are taking as a tolerance here. So now, aside from beta, we are finding that R1 can change, R2 can change, and RC can change, and RE can change. And these changes will obviously cause changes in or variations in the bias current, as an example, variations in ICQ. So now, so far we have been saying that circuit number 2 is very robust. It has a negative feedback and it reduces sensitivity to beta. And circuit number 1 is highly sensitive to beta. But what about the impact of resistor tolerances? Is circuit 2 still better than circuit 1 in terms of sensitivity to these changes in R1, R2, RC, RE? Is circuit 2 still better than circuit number 1? So what we can do is simple. We can vary, for example, R1 we can make it 5% higher, R2 R1 5% lower. Similarly, all the resistors can go 5% higher or 5% lower. And through these combinations, we can find out how large can the collector current can go and how small can the collector current go, right? So we can look at the two extreme values of collector current. For example, if you want to look at, let's say, circuit number 2 and you want to calculate the maximum IC, what is the maximum IC that I will get? Well, the maximum IC you can see you will get if you take R2 5% higher, R1 5% lower, because what it will do is it will make the base voltage maximum, and then you take RE 5% lower, and the effect of RC is negligible. So if you take this combination, you will get IC maximum. Similarly, if you take the opposite combination, you will get IC minimum, right? And in circuit number 1, we have only one resistor, so if you take RB, which is 5% lower, then you get IC maximum, and the opposite will give you IC minimum here. So like that we can find out what is the variation in IC max, what is the variation in collector current in circuit 1, and what is the variation in current in circuit number 1 and 2, and we can compare them. And we can see which circuit is more insensitive to the resistance tolerance here. So, we are looking at resistance tolerance here. Which circuit is more insensitive to changes in resistance? We already know the circuit number 2 is very good with respect to changes in beta. So, let us look at the numbers, right. So, we have made 5% tolerance here. So, look at that 5% tolerance. All the resistors can have 5% tolerance. So, let us look at circuit number 1. In circuit number 1, the current can become as large as 1.86 milliamperes from an initial value of 1.76 milliamperes. It can become 5.25% higher. Or the collector current can go as low as 1.68 milliamperes here, or about minus 4.75% here. Can decrease from its typical value or nominal value. So, let us look at circuit number 2. In circuit number 2, the collector current can go as high as 1.94, which is 11.46% high, can go as low as 1.56, which is 10.38%, minus 10.38%. So, what do we find? We find that circuit number 2, this is our circuit 2, the voltage divider bias is, and this is our circuit number 1. The voltage divider bias, this circuit is more sensitive. Is more sensitive to resistance tolerance. Note that same 5% change is taking place. In the circuit number 2, we get as large as 11.46%, while here we get 5.25%. So, circuit number 2, the voltage divider bias is more than twice as sensitive to changes in resistance values, and they will always be all resistors will never have a constant value. The values will always will be 5%, 10% depending on the kind of resistors that we are using here. And the reason is easy to understand. If you look at circuit number 1, the ICQ value depends only on one single resistor RB, and so 5% change in RB will result in 5% change in ICQ. On the other hand, in circuit number 2, the ICQ depends on R2, R1, RE, so it depends on 3 resistors that are there here, and each resistor will contribute to changes in ICQ. So, there are 3 resistors in circuit number 2 which decide the value of ICQ, resistor R1, R2 and RE, and that is why any variation in those resistors will have an impact on variation in ICQ. So, our circuit number 2, the voltage divider bias, which is called the best way of biasing or the most robust circuit, we find that it is not so robust. In fact, the variations in the resistors cause much larger change in the bias current as compared to circuit number 1. So, that is what we were commenting, that whenever you gain something, you lose something here. So, in circuit number 2, what we gained was insensitivity to beta, and beta insensitivity is very important. But what we lost was the sensitivity to the resistors that are there in the circuit here. So, the circuit has become more sensitive to the tolerance, the variations in the resistors that are there here. And let us look at one more thing. The amplifiers are supposed to work over a certain temperature range. So, nominally we calculate the bias currents and the gain and everything at a room temperature, which we take as 27 degrees Celsius here. But let us look at the base emitter voltage here. The base emitter voltage VBE, we know it approximately goes as minus 2 millivolt per degree Celsius here. And for many of the commercial applications, the temperature range is 0 to 70 degrees Celsius here. So, what it says is that if we look at this entire range of temperature, VBE can vary by approximately 2 millivolt multiplied by 70. So, it can vary as minus 140 millivolt, right. Now, this variation in VBE will cause variation in ICQ, right. So, what we are saying is variation in temperature will result in variation in base emitter voltage. Now, variation in temperature can also result in variation in current gain. We are not, we have already seen how the two circuits match with each other with respect to beta, but let us look at the variation in the base emitter voltage here. So the base emitter voltage is not a fixed quantity, it will change with temperature. And as the base emitter voltage changes, ICQ will also change. So how do the two circuits, circuit 2 are voltage divider bias and circuit 1, how do they compare each other here with respect to changes in delta VB? So let's look at that here. So this is what we have. So ICQ in the circuit number 1. So this is circuit number 1. So ICQ is beta VCC minus VB by RB. So we can write this delta ICQ is minus delta VB by RB. We are only looking at changes in delta VB. And it's always, one should not look at absolute values here, one should look at the percentage difference here. So delta ICQ by ICQ comes out to be minus delta VB by VC minus VB here. All right. So note that in this case it will be equal to minus delta VBE, and VCC is 9 volt and 9 minus 0.7, so that will be equal to 8.3 right here. Same if we go on the circuit 2 side here, ICQ is approximately equal to VCC R2 by R1 plus R2 minus VB by RE here, and in this case also we can write percentage changes equal to minus delta VB by VCC R2 by R1 plus R2 minus VB here. So this will be equal to minus delta VBE, and the base voltage is 3.87 minus 0.7 here. So this will be equal to minus delta VBE by about 3.17 here. So you look at the sensitivity of the two circuits to changes in base emitter voltage here. This is delta VB is the same in both of these cases. It is divided by 3.17. In the other case is divided by 8.3 here. So again we find that circuit number 2, the voltage divider bias is twice as sensitive to changes in base emitter voltage as compared to circuit number 1. Right. So in this case also we find that we are losing something, that by creating a voltage divider bias and by achieving beta insensitivity, we have actually created more sensitivity towards any changes in base emitter voltage. So to summarize, what is being said is that when you compare two circuits and whenever you gain something, so here circuit number 2, so if we can write about circuit number 2, the voltage divider bias here. So yes, in voltage divider bias we get beta insensitivity, right? That is obvious, and every book, everybody talks about it, that circuit achieves beta insensitivity. But what we get is more sensitive to, but it becomes, the circuit becomes more sensitive to variations in R. Variations in R due to tolerance. The circuit becomes more sensitive to variations in VBE because of let's say changes in temperature. So we achieved something positive, but we lost also something in the process here. So that's why as an engineer we should always be aware of that there are trade-offs. That there are always trade-offs when you try to improve something. Very often, I'm not saying that it always happens, but very often you end up losing something. And as an engineer, you must be aware of what is it that you're losing in the process of achieving something which is there here. And in fact, in the next lecture, we will see that yes, you gain beta insensitivity, but you end up losing a lot more. Besides these things that we discussed today, you end up losing, for example, the voltage gain. You end up making, for example, the input resistance becomes beta sensitive. So note that the circuit here, if we look at this relationship IC equal to beta IB is always valid, right? So now we have made IC in the second circuit, we have made IC very stable. But note that beta is still varying. So what we have done is we have made base current unstable. So now what would happen is IC will remain fixed as beta will change, but then IB will change here. So actually what we have done is we have not solved really the problem of beta insensitivity. We have transferred the problem to the base current. Now the base current becomes very highly variable. While in the first circuit, what was happening is this relationship is still valid here. So IB was stable, and as a result of variation on IB, IC was varying. And in the next circuit, IC is stable, and a variation in beta results in variation in IB here. Now variation in IB is also a problem, because note that R pi, for example, small signal parameter Vt by IB depends on the value of IB here. So now R pi will start varying. So as beta will change, R pi will change here. Now while in the first case, for example, when IB was fixed, then IC was changing, and GM is IC by Vt, right? And gain and everything depends on GM here. So what we have done is we have made some parameters beta insensitive at the cost of making something else which is more beta insensitive here, or more beta sensitive here. And there are other losses that we encounter in the process here, right? So today we saw that with respect to bias point, if you make the circuit more beta insensitive, you end up making it more sensitive to variations in resistor and variations in VBE. All right, so let's stop here.